Okay, yeah, thank you very much. Thanks to the organizers for setting up a fantastic conference, and I really appreciate being invited here. Let me start with 2 words of apologies. So, on the one hand, I will have to finish in time because there's some appointment at 12 I have to go to. If you want to discuss anything or have questions, please let me know, if necessary, by email. In the afternoon, we shall find some time, just I can't help it. I will have to run a bit after finishing the talk. I'm sorry about that. The second apology is, well, you know, I'm slightly schizophrenic person, so I'm half mathematician and half physicist, and sometimes these 2 parts of my personality are fighting with each other, and it was a bit the case when preparing this talk. So, okay, I have to. So as this plan indicates, there is going to be a physics part and a math part. I'm starting with some questions from physics. The middle and a bit like main part will be actually mathematics mostly, or mathematical physics in some parts, and then I shall return to physics in order to use the mathematics that is called Analytic Langlands correspondence, or its quantum deformation, in order to propose answers to the questions that I started with. So let me start with a question. So one of the questions is about the integrability that has been found in various very important developments in N=2 supersymmetric quantum field theories in 4 dimensions. And this is in particular an outgrowth of this famous work of Seibrook and Witten, which led to sort of the discovery of these integrable structures. And in a very sort of tiny nutshell, first way to see it is to observe that the Coulomb branches of vacua of these supersymmetric quantum field theories, they have all the necessary geometric structures in them that you need to build a complex integrable system. Here understood as basically in the guise that is provided by the Liouville-Arnold theorem in the real case, but now we complexify it, namely in the form that we have a manifold which can be represented as a torus vibration. So here, the base of this torus vibration, there's a caricature on the picture that we see, yeah, here. That is the Coulomb branch, but basically the structures of the Coulomb branch tell us all that we need to know in order to define in a canonical way the tori that we put over each point of this base manifold. And this basically, I mean, a kind of hands-on coordinate-based description is here on the slide. Namely, as I assume you will know, the low energy effective action of these field theories on the Coulomb branch, it is all encoded in a single holomorphic function called prepotential. We can take the matrix of its second derivatives, and by this we can form this complex torus like so. Therefore, I mean, there's more to be said to make this a full-fledged like mathematical story, but I think it gives the main idea of why basically the structures of the Coulomb branch basically canonically encode also its enhancement to a full-fledged torus vibration, which is what we can also interpret as a complex integrable system. Well, and then there's a lot of like very important subsequent developments indicating that this is not only a story about, say, relations between supersymmetric field theories and classical integrability, but it gets actually deformed in a natural way in various circumstances into relations to quantum integral models. And I mention among many works that deserve to be mentioned here, some pioneering works of Nekrasov and Shatashvili, who very importantly pointed out these directions, and in particular proposed the deformation of these prepotential that can encode spectra of the quantum integrable models. However, I think a question has remained open for a while now, namely, can we actually see the full structure of quantum integrable model in terms of n=2, d=4 supersymmetric quantum field theories? And what I mean by full structure is Well, if we are coming from physics, then a quantum integrable model should also have a Hilbert space defining, together with the commuting Hamiltonians that characterize the integrable structure, defining a spectral problem. And so we would like to study the spectral decomposition, but it crucially depends on having an a priori choice of the Hilbert space. In some cases, we can be lucky and there is a natural choice, and we can sort of see this was indeed part of what Nekrasov and Chatashvili did. But so far, there didn't seem to be a canonical way of proposing a Hilbert space structure and then having an associated spectral decomposition related to n equals to 2, d equals 4 supersymmetric quantum field theories. So that is one of the questions I want to pose. Another one goes in a somewhat different direction, although there are relations to the previous story, which, however, I don't want to discuss here. Chern-Simons theory has been a famous example of, well, many interactions of physics and mathematics. Just think of the theory of knot invariance, Reshetikhin-Turav, Witten, and so on, all these famous works. However, these are Chern-Simons theories associated to compact groups. And well, it has been around for a long time that there should also be an interesting story in the cases where you replace the compact groups by non-compact groups, which can be either complex or maybe real. In this case, we're interested in complex groups. So we want to study a particular case of what is called complex Chern-Simons theory, defined by this action. Okay, I did write here the probably well-known Chern-Simons action. So we're considering G connections on 3 manifolds, and note, okay, we have here a particular range of the parameters. That's not the only one that can be considered, but that's the one we shall be interested in. And for me, I think one of the most interesting motivations behind is that there is the perspective, which I think still isn't like fully explored, to apply the complex Chern-Simons theory to three-dimensional de Sitter quantum gravity. This is subtle because there are also, well, old observations that this cannot be like a complete direct relationship, say in terms of a one-to-one relationship, despite somehow the relation between the actions that Witten has observed. However, a scenario that seems to be still promising is that you can find inside of the Chern-Simons theory somewhere sectors or parts or components that have a direct relation to de Sitter gravity. Anyway, now let's make it a bit more concrete and a bit more mathematical. What this theory should do is, I mean, we're studying 3 manifolds. We can study 3 manifolds of the form Riemann surface times interval. And then what it should do is to assign to the Riemann surface, I mean, it's just the idea of, say, quantization in the Hamiltonian framework in physics. So then you're fixing a spatial slice, which is here represented by that Riemann surface. And to that Riemann surface, it should associate some algebra of observables, which would here be interpreted as Wilson lines. And then a Hilbert space, which should be a representation of the algebra of observables. That's what we expect. That's sort of the standard expectation from physics. What the algebra of observables should be, basically, I mean, that's a purely algebraic question. And for this, basically, we can rely on various investigations of complex Chern-Simons theory. In particular, it's Hamiltonian quantization. That is relatively easy to, say, predict. It should be the famous Skene algebra. We shall restrict to the group SL2 from now on, at least most of the time, almost exclusively. And then it has generators which are associated to loops on the Riemann surface, simple closed curves on the Riemann surface. And the relations can be figured out using the locally applied rules for resolving, say, intersections in a projection of these. I mean, here this indicates sort of the order in which you take a product of operators, and then by resolving this intersection in this or that way, you're defining another loop, and this is the loop appearing in the product of L1 and L2. That's roughly the idea here. But yeah, but the main question, which to my knowledge up to now wasn't answered, or well, there were proposals, but there's going to be a new one, is, yeah, what is the Hilbert space here, and how does it carry a representation of the skein algebra? Furthermore, what one would hope for is that generalizing what has been found for compact gauge groups, there should be a holographic relation to conformal field theory. But what is this conformal field theory, and how does this holographic relation work? So these are two types of questions which I believe from physics can motivate the math that I want to discuss right now. So now I'm making a switch to math and want to, okay, so here, yeah, that's the proposal. Analytic Langlands correspondence together with its quantum deformation gives the mathematical background which provides, well, which we can use as groundwork for answers to these questions. All right, switch to math. We want to study now the integrable systems which are relevant for a relatively large class of n equals to 2, t equals 4 supersymmetric quantum field theories. Is clarified or discovered in the work of Gayotto, Moore, and Knightsky, and these will be the Hitchin integrable systems. Again, we want to keep life simple, and well, what we can do for now is for a special choice of the underlying gauge group. It is again G equals SL2. And well, I had been talking about a Riemann surface, so again, we fix here once and for all a Riemann surface that we call C, and have in principle any genus and any number of punctures. So we want to define the complex integrable system. Well, that's a famous result of Hitchins. We can consider the moduli space of pairs, which consist of a holomorphic SL2 bundle on that Riemann surface, and a so-called Higgs field. Well, if you want, it's a one form, matrix valued one form, locally defined on the Riemann surface. K is the canonical bundle of the Riemann surface, so the holomorphic 1,0 forms. This space has a canonical Poisson structure, and okay, I just tell you that that is relatively standard and well known to define. It has a Poisson structure, so thereby we have already important ingredients for making it an integrable model. What we need now is the definition of the Hamiltonians which commute with one another. And this is provided by the so-called Hitchin map. We're taking the trace of that Higgs field squared. And what is this? If this is a one form, the trace, matrix model one form, the trace of this here will be a quadratic differential. So we can expand this function here, which is function still on the Riemann surface, with respect to a basis for the space of quadratic differentials, that is these H0 C comma K squared. So the basis elements are denoted here by QR. This is where the Z dependence is. And the coefficients then naturally are functions on our moduli space. They depend both on the choice of phi and the holomorphic bundle. These are our Hamiltonians, and yeah, what Hitchin proved is they're Poisson commuting with respect to the natural Poisson structure that this space has. So we have 3G minus 3 plus n Hamiltonians, and if you, using Riemann-Roch and so on, compute the dimension of this moduli space, you find this is just half of the dimension of this Hitchin moduli space. So a very nice paradigmatic complex integrable system. Good, so the first steps towards the quantization of this integrable system were done in this very important and influential work of Bailyn and Drienfeld on the so-called geometric Langlands correspondence. Namely, the output I put here in sort of very meager words of their constructions was a proof of existence of differential operators on a square root of the canonical line bundle on the moduli of holomorphic vector bundles on C, right? So this is what parametrizes, that's the space which parametrizes the choice of the holomorphic vector bundles here in the Higgs pair. So this is a space, a complex manifold. Well, it has a complicated structure, but never mind. And it has a canonical line bundle. We take the square root, and these differential operators naturally act on that square root. These are perhaps technical details that you don't need to bother about, just this is understood. Well, these differential operators, so their claim to fame, the most important properties are these two. Namely, on the one hand, they are commuting, as you would expect, as it should be the case in quantization of an integrable system. That's point one. And second, must be an indefinite relation to the classical Hitchins Hamiltonians that we introduced here. Namely, they have the classical Hitchins Hamiltonians as their symbols, which means something very, very simple. So if here our HR, okay, well, maybe I don't have fonts here on the board, so let's put het for the quantum guys. They're going to be of some form like FRS of X. So this is, say, moduli for the moduli of holomorphic vector bundles, and then we have here some dxr, dxs, sum over rs in some local coordinates, and producing the symbol or extract. I mean, there may be lower order terms here, and extracting the symbol would simply be the game of replacing these guys with functions on the fibers to the cotangent space, which can be identified with functions of this Higgs field PS. So some FRS of X. So this should be the classical guys. Okay, so this is the relationship which simply says, okay, if I dequantize, if I back to the classical case, we're recovering what we had before. Okay, so that's the setup. And let's now go deeper into the quantization. Namely, we want really now, having commuting operators, we want to set up a spectral problem. For a given collection of, say, complex numbers, what we can do is to consider the pair of complex conjugate eigenvalue equations like so. So we can ask for a function, well, properly speaking, it's a section of a bundle of densities where we take here these half densities on the moduli of bundles, and we tensor with the anti-holomorphic counterpart. So that's basically something like the absolute value. And yeah, we can look for sections of that line bundle which satisfy this pair of differential equations. Well, for all values of the index R running from 1 to D, and D was the dimension of the base of this Hitchin vibration. Okay, so yeah, and then we can look for solutions. I mean, of course, locally we can solve these holomorphic equations in terms of holomorphic functions, say, called psi k. Likewise, so this we can locally solve by anti-holomorphic functions like the psi bar L here. But what we then, as the first and basic requirement, would like to have is that we can form combinations. So these by themselves, let me stress, this is very important. They won't be single-valued for themselves because there are singularities which actually can create a lot of headaches here associated to the so-called wobbly bundles. Never mind if, so these are bundles admitting nilpotent Higgs fields, and at these singularities, the Hitchin Hamiltonians have singularities, which means that the solutions to these equations can have monodromies around these singularities. So even the condition of single-valuedness of such expressions is a highly non-trivial one, because one thing is clear, you will have to find non-trivial linear combinations of this form in order to achieve single-valuedness in the first place. So that's the only chance to get single-valuedness, given that there are singularities with monodromies around them. Okay, so the wish list for the solutions of this form that, I mean, are perhaps kind of obvious to write down is these solutions should be smooth away from the singularities. They should be mild, of course, the singularities not spoiling square integrability. Okay, but I come back. Then single valuedness, this was sort of conditions that were studied in some older work of mine. And so the new twist to which I want to come now was to require also square integrability. And what I anticipated here, there's a very natural L2 space, which we get basically for free in this setup, which defines the scalar product with respect to which to demand square integrability. And that was sort of a main new ingredient in the work of Ittinger, Frenkel, and Kashtan on what is now called the Analytic Langlands correspondence, which I now want to discuss. Good. So I want to discuss in a very schematic form Langlands type correspondences. And I don't have the time to really properly introduce what is geometric Langlands correspondence on. But the cases that are relevant here, I can make more precise. So, okay, I stressed already, single valuedness is already very restrictive. And already in 2017, I had proposed a conjecture that the single valued Hitchin eigen D-modules should be classified by what is called real SL2 operas. There will be a whole slide about what real SL2 operas are, but for now, as a simple first introduction, we can think about differential operators here of the second order, like so, which have to be well defined on C, which means, okay, these T of U's will have to transform from chart to chart by Schwarzian derivatives and so on, having real monodromy. This is a very severe restriction, right? So let me motivate a little bit. Oh, that's the wrong way. Here so far, a priori, the E's were arbitrary complex numbers. What we expect with our quantum mechanical experience is that if we require square integrability, there can be discrete sets, perhaps, which really appear in the problem defined by having, well, smoothness plus square integrability, a discrete spectrum, we would call it. However, as I stressed already, the single valuedness is very restrictive, and the proposal here was this already basically produces a discrete spectrum in one-to-one correspondence with what is called real operas. I will explain why the set of solutions to having real monodromy on a Riemann surface produces a discrete set. And the important step taken then in the work by Ittinger, Frenkel, and Kashtan was a considerable strengthening and generalization of this first proposal to a relation, to a correspondence of the following type. We can look for single valued and normalizable with respect to this Hilbert space structure. Eigenfunctions, I mean, I'm using here fancy language, eigen D-modules. This is just to indicate the relation to what is called geometric Langlands. There people talk about D-modules. We don't really need to talk about D-modules here. Eigenvalue equations, the proper translation in our context. So, however, there's another important ingredient that they introduced, which indeed is very useful. These are the so-called Hecke operators. I don't have the time to introduce them properly, but you can think about averages over modifications of the bundle, which are supported at points of C. And there's a very precise definition. These are basically non-local operators integrating the wave functions over some subvarieties in the moduli of bundles. So these are the Hecke operators, and these can be shown to produce another family of operators which commute with the Hamiltonians and thereby refine the spectral problem. Much better functional analytic properties, they're compact in particular. This is why they're very useful in the formulation of the spectral problem. And their proposal was that then, okay, if you're asking this refined and in some sense rigidified question, there should be, loosely speaking, a one-to-one correspondence with the real operas. There will be a slide about real operas next. So we want to make our ideas what these guys are a bit more concrete. But yeah, that's the gist of it, namely that basically we have geometric objects classifying the solutions to a spectral problem. And it is in a close analogy, but a non-trivial analogy to what is called geometric Langlands correspondence, which I don't want to explain. Okay, in passing, I just wanted to mention, but that's really more an aside, that, the previous proposal, which definitely was not fully satisfactory yet. However, it could well be that in the end of the day, basically, you know, the same things appear here, at least for SL2 on the right side. So ultimately, I think it should be true that the sets of solution here on the left side are also equivalent, which could well be true, and there are some examples indicating that it is true. However, this, due to these additions of Ittinger, Frenkel, and Kashtan, is also a more tractable problem. So for this, there are some, I will quickly mention, there are some cases where this has been proven. In general, it's a conjecture. All right, comments about real operas. So I introduced real operas as differential operator of this form, but they have a close relation to hyperbolic metrics or uniformization. So we can start, but that's only the start, with the so-called uniformizing opera. And it's very classical. I mean, 19th century mathematics, that differential operators of this form have to do with uniformization. Namely, the relation in a nutshell is we can look for the solutions to this differential equation defined by what we call an opera. I should have written here also the anti-holomorphic equation. They should both be satisfied. But yeah, from its solution, which we denote here phi 0, we can form this object, and we can easily check that this is a metric of constant negative curvature. That is the uniformizing metric. If I pick here the right T0 and the right solution, there's a unique T0 and a unique phi 0, basically, which would give the uniformizing metric. Now, here's a picture, for example, how it will look. We can use the solutions to this differential equation to also to produce the map to the upper half plane with its constant negative curvature metric, which makes the uniformization concrete and explicit. It was known for a long time, and this was historically even the first approach to uniformization problem, that you need real monodromy of this differential operator in order to get the desired solution here. So what you have to do is sort of to fine-tune its coefficients in order to achieve real monodromy. And this was an approach that was tried at the time to prove uniformization, which later was abandoned because somehow it was hard. Anyway, by now we have, all this is backed up, of course, by classical theorems, and we're ensured the existence of this T0 and the corresponding phi 0, which are associated to the constant negative curvature metric, which is canonically associated to the complex structure. However, well, okay, I mean, in that scheme, in that scheme here, well, we have identified one particular example of a real opera. This can hardly account for a spectrum like we have defined here. We need more. Then there is also by now classical and I think reasonably famous story with contributions of Faltings and Goldman and so on, how to get and classify all real operas on Riemann surfaces. And sort of a pictorial way to represent the outcome was not the way it was originally formulated, is we can consider, instead of the uniformizing metrics, mildly singular ones as well. Namely those which have singularities of the type we find at the boundary of the Poincaré disk along lines that are embedded in the surface. So roughly speaking, there is an operation that is called grafting. It has originally a different definition, but I'm sort of translating it into nice pictures which fit on one slide, which amounts to inserting basically pairs of trumpets. So we cut open the surface along a geodesic, say, and then here we insert a part of the Poincaré disk with here sort of this boundary being the boundary where the metric diverges, and this boundary being some geodesic of a finite length. And yes, the results the result of Goldman is that all real operas can be obtained by applying this operation, and hence, basically, it follows immediately, they're classified by counting singularity lines and a convenient mathematical encoding of this collection of lines on which singularities may occur is the notion of measured laminations. So we want half, okay, there's some important fine print here, some important subtleties, which, however, I want to avoid if possible. But these are understood. This is not a... It's just, okay, laminations, just think of collections of simple closed curves which don't intersect themselves, and you just count them. That is basically a translation. It's just because this is a standard terminology in the literature, I was adopting it. But it's really nothing fancy. It is these collections of curves with the weights, which, so you can have, for example, you can repeat this operation, of course, n times. Then you find n singularity lines, which, however, are basically running parallel to each other. And these weights here, these half-integer valued weights, count how many you have, for example, in a given class, given isotropy class of the original surface, I mean, of a curve in the original surface. Okay. Good. So how then can we recover the eigenvalues? You know, okay, where do we stand? We have postulated, proposed this correspondence between real operas and eigenstates of the Hitchin system. I told you how to classify the real operas, which amounts through this correspondence to a classification of eigenstates. One step more is to tell you for given real opera, which is the classifying data, how do we compute the eigenvalues? Here's the answer. If we have a generic real opera corresponding to some eigenstate through this analytic Langlands correspondence, so if this is the eigenstate psi, which has eigenvalues E1 to ED, then the eigenvalues can be extracted from the opera in the following form. We have to take the difference. Here we could take any opera, but maybe a convenient ground state is defined by the uniformizing opera. We take the difference here of this and this, which is a quadratic differential. We can expand in terms of a basis for the quadratic differentials. The coefficients here are supposed to coincide with the eigenvalues. That's the statement. So that tells us how to extract eigenvalues from the operas. Okay, so to sum up, this basically almost finishes this part, explaining what analytic Langlands correspondence is about. It furnishes a geometric description of the spectrum of the quantized Hitchin Hamiltonians. Maybe the form that I request you to ask in mind is that we're associating to a lamination these collections of curves, eigenstates. Concerning the state of the art and what is proven and what is conjectured about it, there are full proofs of this conjecture, thanks to Ettinger, Frenkel, and Kashtan. But in most cases, it is open. And well, we hope to soon finish. We are getting fairly optimistic by now. A proof with a PhD student of mine, Federico Ambrosino. And for the mathematicians, maybe here is sort of the main message I want to at least mention very quickly. In many approaches, including the one of Ettinger, Frenkel, and Kashtan, these wobbly bundles, those admitting nilpotent Higgs field, create a lot of headaches. You would have to understand precisely how wave functions get singular near the wobbly bundles when you approach them. Our proposal is that there are very different tools. I mean, we're using very different tools, very different methods compared to Ettinger, Frenkel, and Kashtan, called separation of variables, but we also use the Hecke operators of Ettinger, Frenkel, and Kashtan. And it looks very promising that thereby we can circumvent basically needing an explicit study of the wobbly locus. The reason being, the separation of variables gives a unitary integral transform to a simpler problem where we can control, for example, normalizability in a simpler way. And thereby unitarity saves the day for us. And okay, so this just you can ask me about if you're interested, but I don't have the time to go into these mathematics right now. Good. I now want to talk about a quantum deformation thereof, where well, I didn't do it here, but in other, no, but here I did it yeah, you can argue how appropriate the word quantum is. Some people use it in particular. It has a, however, difficult to explain relation to what Gatesbury and company call the quantum geometric Langlands correspondence. The main idea, namely, is the same, that we can observe that the so-called Knishnik-Zamolodchikov-Bernard equations from conformal field theory serve as natural deformations of the Hitchin eigenvalue equations, which were the main players in the previous story of analytic Langlands. So very schematically, these equations look as follows. We now take care also of the dependence with respect to a choice of the complex structure on the underlying surface. So the z's here are coordinates for the moduli of complex structures on the Riemann surface. They are now also considered as variables. And these axes here, these are again just coordinates for bund G, the modular of holomorphic vector bundles. And the KZB equations can be considered as heat type or Schrödinger type equations of this form, where these here are basically, again, the Hitchin Hamiltonians we had seen previously. Heat or Schrödinger type depends, by the way, on whether this k+2, which is sort of the standard CFT notations, is real or imaginary. We're interested in the imaginary case, where, nicely enough, this is of Schrödinger type. Will play some role in a moment. So here's the sketch, the quick sort of main idea why this equation is a deformation of Hitchin's eigenvalue equation, which is slightly non-trivial. It's in the following sense: if you approach here k equals -2, which is of course making degenerate this equation, then you can argue that solutions need to behave in the following way. There's some singular part of this form e to the 1 over k+2s, and then something non-singular when k approaches -2. And just by plugging this as an ansatz into the KZB equations, you will find that these two data which appear here, characterizing the singular and the non-singular part of the behavior here, have to satisfy this system of equations, where you see the Hitchin eigenvalue equations reappearing, like here. That's, I mean, two lines of computation, very easy to check. And on the other hand, this S is nothing but a potential for the eigenvalues, which, however, then will vary with Z. This, by the way, is also what Nekrasov and Chatashvili introduced as their, what they call the Yang-Yang function, and this is how it appears here in passing. This is, okay, KZ was for genus 0 originally. Bernard did the generalization for genus 1 and higher, and I think therefore it is appropriate and customary to call it KZB. Good, so yes, we can slightly modify, right, by introducing this parameter, which is, I didn't write it here, but it is related to this k+2. We can modify somehow the power of this bundle, defining our L2 space, and you can check, I mean, at least formally, it's easy to see that this then is a Schrödinger equation, and that this here is really defining a parallel transport. So, all right. But the main point really I want to stress here is that what we're looking for naturally will be single valued and ideally also normalizable solutions in this Hilbert space, solutions to KZB. Lowercase s, where's lowercase s? Here's s. You find it anywhere else? Sorry. Which lowercase s? So is this one? Okay, so this here is the parameter. Okay, it was too brief, I'm sorry. This is k+2 over I is s. Good, this is the problem which I propose as a generalization to this eigenvalue problem for Hitchin Hamiltonians, namely to find single-valued normalizable solutions to KZB. And yes, I hope to have motivated why it's a natural quantum deformation of this problem, of the eigenvalue problem that we had in the Langlands correspondence case. Yeah. Yes, we come back to it. Yes, that is the space. Now we deform it slightly, right? And now we're looking, we will come back to skein algebra actually, which will play a very important role. Good, so we do know some single valued function satisfying KZB. Namely, well, it was expected for a long time on the basis of physics arguments that this should be exactly the correlation functions of the H3 plus Wessel-Witten model. Okay, this is a statement I just have to flash here without having any chance to go into any further details. There's a CFT whose solutions are expected to be exactly the type of solutions to KZB that have these two properties, single valued and normalizable, and which are naturally defining this very non-trivial functions which depend both on, say, the Bun-G coordinates and the moduli of curves. Well, this is really, I mean, by some order of magnitude more complicated functions than what you find in the compact case, I should stress. But it's not easy to construct such functions. But what I want to stress, so here, okay, this is sort of the way how formally a physicist would propose a definition in terms of a path integral with the action being the Wessel-Witten action, but we're replacing in the argument the compact group element that we have in the compact case by the 2x2 matrix representing elements in the hyperbolic 3 space. And then we inserted here something called vertex operators, which are particular functions of this matrix H, which represents the fundamental fields of the theory. And we're forming a kind of generating function out of these variables X, which turn out to have relations as well with, say, coordinates on the modular of holomorphic vector bundles. But that takes a bit of time to explain all this. So just, you know, these guys solve the equations we want. That's the main message. And there's a construction for these functions if we're able to construct this path integral. That's sort of point 2. And yes, due to some very recent progress, which is very nice, I find, in probability theory, generalizing what has happened in the case of Liouville theory, the work of Kupian, Rodez, Vargas. So this has, well, then continued in a whole series of works, basically putting the Liouville conformal field theory on rigorous grounds and well, I guess partly motivated by stories that, as I'm telling today, then Guillermo, Kupian, and Rodez were actually able to make rigorous sense out of the path integral that we wrote here, which basically amounts to providing a rigorous definition of the functions that we're after. So these are honest math objects now, and not just sort of a physicist's hope. These are rigorously defined objects, thanks to these people. But again, we're having, I mean, this basically, you know, you can study, for example, here the limit when this parameter k goes to -2, you will find a relation to uniformization. Okay, I don't have time for this. But again, the main point is we just have a single vector, according to our philosophy, in the Hilbert space that we have defined. How to get more is the obvious question, and this is what is addressed next. The main player, the main name of the game is we're getting them using the Linde line operators. So these are, that is sort of the schematic view on them, these are operators which we can make to act on H3 Wessel-Witten correlation functions, which are labeled by the same data that we've seen before, these measured laminations or collections of simple closed curves on the Riemann surface. So, okay, good news, the labeling data already works out, it's the same. I can only sketch the idea of definition. This has a long history going back to Eric Verlinde's work on the famous Verlinde formula. It's a kind of natural tool that you usually apply to conformal blocks. You insert pairs of degenerate fields into a given conformal block. You perform analytic continuation with respect to the position of one of them, performing a loop on the Riemann surface, and then you return to the original position where the sort of partner has has remained and you re-annihilate it, and the result is something that basically modifies the original conformal block into another one. So this is a kind of canonical way to define, to get module structures on spaces of conformal blocks, which you can apply in many situations. And you can then combine it with holomorphic factorization in order to have something related on the level of correlation functions. That's the idea, that's the basis of the proposal of Davide Gaiotto and myself. We can use these things now on this non-holomorphic level of the correlation functions in order to get one correlation function out of another. So thereby, indeed, we can generate an infinite family of such correlation functions. I'm coming to this question in just a second. So we can hope this will give an infinite set of solutions to our problem, very naturally. Okay? Well, it's related. Actually, you know, there is something, I mean, as you're asking, in the theory of projective structures, especially real projective structures, I was using this word because there is an operation called bubbling, and I claim it's really the classical limit of what I'm talking about here. I mean, it's about branch projective structures, and you can create sort of two branch points by an operation called bubbling. There's De Roy, Casamilia, and so on. There's a paper doing the geometric classical story, which is very beautiful. And they also explain how, you know, by doing bubbling, a continuation, and then sort of re-annihilation, you can create the grafting. This is, I mean, this is not, I believe, this is what I claim here, really the geometric counterpart of what we described here in CFT terms. Good, and here comes now a non-trivial claim, which I don't have the time to explain any details about. This is what did require a certain amount of headaches, which is not a trivial statement to obtain. You have to really carefully look at the correlation functions, study their singular limit in this when the level k goes to -2, and you have to combine somehow some arguments related to projective structures, real operas, with some arguments about, say, semi-classical limits of correlation functions or conformal blocks in the CFT. There's a certain amount of arguments that need to be combined in order to arrive at this main claim, which is these Valinde line operators. When we go, this is unfortunate, this should be S, basically. When we send S to 0, we're returning to the case of analytic Langlands. So this should be basically S here. And our claim is then we reproduce the grafting action. So it is exactly, it is really, this is the quantum grafting in this sense. Yeah, you can B going to infinity. No, yeah, B going to infinity is S going to 0, exactly. Okay, good. I should probably slowly come to an end, but this is, okay, so this is here now, to summarize, a proposal. You know, some parts, as I stressed, are rigorous. This part is not yet rigorous math, let's be clear and honest, but I think these are, in my mind, fairly solid arguments, but it's not rigorous, to be sure. Yeah, but with this, we do have a proposal for what we could call quantum analytic Langlands. And now I want to return to the question, yeah, what does it give us in terms of the two problems, namely complex Chern-Simons on the one hand, and the integrable structure of n equals to 2 supersymmetric field theories on the other hand. So I start with the former. This is just, again, a summary. Basically, sort of schematically, what we call quantum analytic Langlands amounts to a correspondence between the laminations and KZB solutions. And well, here comes sort of the non-trivial conjectures that we're making in order to really have a precise analog. But these are conjectures for now. An analog of what in analytic Langlands context is proven, at least in some cases. Namely, the idea is that we want to interpret these now as wave functions in the Hilbert space that we had defined, which is very natural in this problem. This is now the Hilbert space that we propose as part of a definition of complex Chern-Simons. Okay, that's the definition of proposed definition of Hilbert space. And then, yeah, we have here, this is sort of the main conjecture that we need, namely that whatever we're creating with the Verlinde line operators is normalizable, and that the set that we obtain in this way is complete in that Hilbert space. If this is so, then it's basically automatic that we thereby make the Hilbert space a module of the skein algebra. So thereby we would have achieved a definition, a construction of the main structures that we need to construct complex Chern-Simons theory, or of some main structures. You may ask more, but some main. Okay, so I would therefore like to propose that we can quantize complex Chern-Simons theory on the basis of what I call quantum analytic Langlands correspondence. That's sort of point one. And yes, now back to integrability of n equals to 2 SUSY QFT. What we want to consider, and here I have to assume some knowledge by the participants in the audience, what this here is, so we're considering n equals to 2, d equals 4 supersymmetric quantum field theories of the so-called class S. They're parameterized by the choice of the Riemann surface. And in a Lagrangian representation, they would have a gauge group of 3G minus 3 plus n SU2 gauge group factors. Associated is a collection of UV gauge couplings. There can be mass parameters associated to the punctures. And we can put such a theory on a 4-manifold, a Euclidean 4-manifold, like the 4-ellipsoid, which is nice and important because this is a manifold that preserves some supersymmetry. There's a lot of results initiated by Vasily Pastun and then many followers studying localization of partition functions on 4 manifolds of this form. Now, but however, what we want to do is to, well, enhance or decorate that story by introducing defects. That's sort of the main extra players that we need. We can consider disorder type surface defects. They're characterized by a certain singular behavior. So, okay, first it has a support in the 4-dimensional manifold, which is defined by simple equations like so. So they're basically wrapping an embedded 2-ellipsoid of the 4-ellipsoid. And then we can specify or a certain singular behavior in the vicinity of this 2-ellipsoid, which has parameters which I don't want to specify. They're collected in this little s here. It's a boldface S to distinguish it from the other, but maybe it's not so well visible. Okay, so this is one type of defects which has parameters. There's another type of defects which wraps sort of the equator on the other ellipsoid that we can see in these 4-ellipsoid. These are line defects. I stressed these introduce 3G minus, I mean, okay, it turns out, I'm just telling you this, that we have this number of complex parameters associated to the surface defect, which basically parameterize singular behavior of gauge fields plus a certain coupling we can turn on. These are collected in these parameters. We furthermore have line defects, and line defects are famously known in class S theories with this gauge group to be classified again by the same data we've encountered twice before, the so-called measured laminations. And this follows from the work of Droka, Okuda, and Morrison, which started a lot of the stories here. So in total, what does our partition function depend upon? It depends on mass parameters, tau, UV couplings, surface defect parameters S, and lambda, which are the line defect parameters. Perhaps you will already see where I'm trying to go. The big conjecture which I want to propose here, which however should be carefully checked using physics and honest independent computations in the gauge theory, is the following. Namely, there is a certain dictionary between the variables here, where S corresponds to X, tau corresponds to Z. Well, this is basically the dictionary that Alde, Gayotto, Tachikawa, and so on already had, and M's correspond to these parameters, J, the spins, and lambdas are lambdas. I mean, just using the dictionary of Droka, Okuda, Morrison, for which basically partition function becomes equal to wave function. So this is supported by a lot of work which has similar results. However, in all these works which are in the literature, lambda is trivial. So basically the line operators are absent. In this sense, it goes beyond. But however, for our story, of course, inserting the lambdas, as I explained, is very important. Yeah, I suppressed epsilons. Okay, let's. So epsilon, as you will know, right, becomes k plus 2. Epsilon 1 over epsilon 2 is k plus 2. The other way around. Epsilon 2 over epsilon 1 is minus. Not yet here, but here I'm just doing it, right? So in the limit epsilon 2 going to 0, which corresponds to k going to minus 2 in this dictionary, this is what we know is done by the right-hand side, where we have CFT and tools to control it. So we can thereby conclude that indeed here, these guys, that's the main sort of conclusion, become proportional to Hitchin eigenfunctions. So the upshot I'm extracting from this is that these eigenfunctions basically have an interpretation as partition function of a class S theory with surface defects and certain line operators on the other two ellipsoid. So as a kind of philosophical lesson I would like to extract from this, with which I want to conclude, is in order to see really fully all the quantum integral structures like spectrum and so on, well, we really need the interplay of the defects. This is sort of what really. So, for example, the interesting and somehow new ingredient is this grafting or its quantum operation, which in terms of class S is very natural. Inserting line operators is one of the games many people played. However, that it is related to creating eigenstates, higher eigenstates from a ground state in the relation to the quantum integral model is, I believe, a new and quite non-trivial statement. Thank you. I will finish with that.
Your time okay? Is your time okay?
Yeah.
Okay,
there's time for a few questions. No problem. Yes. No, we consider only closed cycles in this context. For this statement, no, but of course it's easy to imagine that maybe that there can exist generalizations of this story in which they. Yeah. No, I think I can guess what you're why you're asking, but for this story as formulated, I don't want open laminations, only closed, but I think it could be very interesting maybe to think if there's a generalization of that story where open laminations play a role. Yeah, well, okay. The Hitchin Hamiltonians and the complex Chern-Simons, I mean, you do have, right, so you do have these functions, right? So it depends sort of in which picture in the quantization. The Hitchin Hamiltonians, you would expect to find in basically a closely analogous to the ordinary quantization, basically as the right-hand sides of the KZB equation. So you would find them there from the point of view of, I think going back to Kolya, namely that you get the KZB equations as a quantization of isomonodromic flow generators. So there are natural classical Hamiltonians in the theory of isomonodromic deformations, which then will serve as ansatz for natural observables of that type in the complex Chern-Simons. So yeah.
Other question?
I have to. Oh, the path integral. Okay, the state of affairs, as I understand it, is the path integral hasn't been defined in full. The famous development that Vasily Pastun has initiated, it considered the localization of partition functions, and basically based on the assumption that the path integral will ultimately exist and is supersymmetric, you can argue that it localizes to solutions to some simpler equations, and this becomes then something that is tractable and definable mathematically. That's sort of the sort of logic that so far applying these developments. Yeah. You mean the R4? It depends on. Yeah, let me go back. Here, yeah, the 4. Yeah, yeah, yeah. No, well, okay, yeah, you have to be careful in how you describe these limit. One way to think about, no, I mean, really it's rather like a decompactification limit where one of these ellipsoids that you see here becomes an R2. So it's basically, the limit I think is best described as a product R2 cross a 2 ellipsoid. And so indeed in this limit, sort of the surface operators would still be wrapped in the 2 ellipsoid, but the line operators would become like strong because they would be wrapping some cycle at infinity in this limit. This is, yeah. Real part is integer. Oh, okay, yeah. I think I understand. Well, I guess what you have in mind, let me, is at the very beginning, right? There's this generalization of complex Chern-Simons where you give this parameter S some real but integer part. Let me just say, very interesting story. I don't have anything to tell at the moment, but it smells a lot like something very interesting should exist there. My knowledge.
As you only consider the case of regular puncture, right? So
yeah.
what about what if we add irregular?
Yeah. Should be very interesting. No question. So, I mean, we haven't studied in any detail generalizations to irregular punctures, but I think it's clear they should exist, and I think they give lovely follow-up projects on that. So, for sure, yeah.
Okay, let's stop here and thank the speaker again.